In this video, we're going to be looking at angles and how we work them in a physics class rather than what you would see in a math class. This sounds something that would be very simple, but it is something that often confuses people in the beginning. What are we going to be doing? We're going to be introducing the symbols that we use for angles and seeing how they are different from what you would see in a math class. We're also going to review, or for some of you, introduce the concepts of sine, cosine, tangent, and how they are used and when. We're also going to look at another unit for angles. So not just degrees, but we're going to look at something else known as a radian. And we're going to discuss their uses, when we use them and when we do not use them. And we're going to apply angles to circles as well as triangles, specifically the rotations of a circle. Why are we doing this? Because the application of angles is a major skill that is used in physics and engineering. Most things that we deal with have an angle involved in some manner, and you have to be able to work with and manipulate those angles to find whatever it is that we're looking for. The terminology and symbols that are used in math are often math class specific, and they're not going to be the same symbols that you see in other subjects such as physics and engineering. The difference in the languages being used is enough to confuse people. So it's kind of like if you speak Spanish and you're trying to have a conversation with someone who only speaks Italian. You can communicate. The languages are very similar. However, there are terminologies and expressions that will not make sense very easily because the languages are different. Same thing with this. When you see what we're working with in physics, you may not make the connection in math class because the language is different just enough that it can become very confusing. Also, we're starting this early on because you need this later on in the course, but when you need it, you need it. So it's kind of like in sports where coaches, long before a big game, often in the preseason, they start working on skills and learning plays that the team needs to have down for the big game. A very bad coach is one who comes in just before the game and says, okay guys, so this is going to be the play that we've never worked on, you've never seen, and here are the skills that you've never worked on throughout the entire season. And we don't want that to happen here either. So we're going to work on some of these skills now so that when you need them later on, you have them. This also gives you time right now to be confused, to seek help, to practice and enforce. So after you see this video, if you do not understand everything, that's totally okay. We're going to be working on that throughout the year. So if we take a look at a triangle in the way that you'd see it in a typical math class often, you'll see that the corners are all labeled with a letter such as A, B, C, and the sides are identified by the corners such as side AB or side CA or side CB. And sometimes you'll even see it written as like, see as symbols, line BA, line CA, line CB. And these all work very well for a math class where you're just dealing with the corners or the corners or the angles of the triangle or any other geometric shape, and you're trying to identify sides based on those corners. Often in the math class, the symbol that you see for an angle is quite literally two lines that draw out an angle. So you'd have angle A, angle B, angle C. And again, this kind of makes sense for a math class, and that's totally fine as a symbol. However, in a physics or engineering situation, we're going to be using a lot of these values in equations. So we'd like to have symbols that are a little more applicable to what we're using. Not only that, but the variables A, B, C are often used for other values. So a lot of times we instead work with Greek letters, the most common of which is going to be the theta symbol that we see right here. However, they could be any other Greek letter, often such as the two shown over here. Please notice that we don't actually have a symbol to indicate an angle for the value. That's because it's a Greek letter indicating that this is most likely an angle or something dealing with angles. Also, when looking at the sides of the triangle, we don't want to use symbols that or values that are indicated by the two ends, saying such as side BA, where it is in fact a line. So instead we use single letters such as sides A, B, and C. Again, this isn't a very big transition, but this is enough to throw people a little bit for a loop when you're not used to the type of language that's being used. You know what you're doing, but the transition from the new context is often something that can throw people for a loop in the beginning. So instead of a triangle where we have sides BA, AC, CB, and an angle of A, we have just triangle ABC, whose sides are ABC, and whose angle at the base is theta. Another symbol that we're going to be working with quite a lot is the Greek letter delta. It's a triangle, and that always means a change in something. It's always a final minus initial. So a lot of times you might have seen this in math class with your slope. We know slope is the change in your y value over the change in your x. Y final minus y initial divided by x final minus x initial. A change is always final minus initial. So that's a very important thing. It's always final minus initial. Whatever the final is or the finals are, initials are, that's irrelevant. Change in position, change in time, change in height, change in speed. It's always your final minus your initial. Sometimes you might have seen the slope as delta y over delta x or triangle y over triangle x, but it's really not a triangle, it's a delta. And that just indicates a change. We're going to be seeing this delta constantly throughout the course because everything is changing. That's what we're studying, when things change. We'll also see this sometimes with angles. If we have these two lines, I could see that I have an angle theta here. And then if my bar moves up, I'd have another angle over here. So this would be my final, this would be my initial, making this specific angle that we see right here the change in that angle, which is why you see a delta symbol on there. We will see this delta with the angles constantly because we're always looking at how something rotates or moves from one place to the other. So to indicate that there's a change in an angle rather than a set value, you'll always see that triangle there. A key skill that you guys worked with in earlier math classes was similar triangles and how to use them to solve for the sides of other triangles that were similar to them. This is a key skill that we're going to be using constantly throughout our course, although not necessarily in the same context. But similar triangles lay down the foundation for other mathematical tools such as sine, cosines, and tangents. For example, if I had these two similar triangles, which means they share the same angle here at the base, and they also have the same angles at all the other corners, then their sides all have the same proportionalities. Which means if I wanted to find side y, it's got to be proportional to 3, just in the same manner that the 50 would be proportional with the 5. So we can actually set up a ratio of sides where I can say 3 over 5 is equal to y over 50. So I can take this side that's opposite this angle and my hypotenuse, say that's 3/5 and set that equal to this opposite side over its hypotenuse, and simply solve. Likewise, if I wanted to find this base here, and I knew that the hypotenuse was 25, I could set up a ratio using these two sides of the triangle, and I could say that 4/5 is equal to x over 25, and simply solve for x. Now, the truth is, this is going to be true for this ratio of 4/5, I should say, is always going to be true for any triangle that has this set of angles to it. So for any right triangle that has this base of this theta, I will have a ratio of 4/5 for this side and this side. Just like before, it doesn't matter what size the triangle is, as long as it's a right triangle that shares this base angle, this side and this side will have the same ratio as 3/5. And so we name these ratios sine and cosine. That's all a sine and cosine has ever been. It's a ratio of two sides of a triangle. And so we will always work with this. So the sine of this angle is 3/5, regardless of the size of the triangle. Likewise, the cosine will always be 4/5, which would be these two guys' ratio, regardless of the actual size of the triangle. The angle happens to be 36.87 degrees, something that we can easily measure with a protractor. And we often will just work with this angle value instead of anything else. So instead of setting up some sort of triangle where we have similar sides, we could just know what the angle is, and then we can just look up what these ratios are. So when you plug into your calculator the sine of 40, basically the only thing the calculator does is looks up on a table, if you will, and tells you what the sine of 40 is. It's not really a calculation. It's just a simple ratio that we have memorized that we can simply use. Back in the day before the calculators, we actually had what's called a trig sheet, and you would just simply look up what these ratios were. You might have already learned that sine, cosine, and tangents are the ratios of the sides of a triangle. And the way this works is if you have your angle that you're interested in and you draw an imaginary dotted line inside the triangle, then the side that's opposite of the line is the opposite side for your angle. The side that is touching the angle, that is smaller than the hypotenuse, is called adjacent. Adjacent just means next to, so it's always the one that's next to the angle. And then the longest side is always the hypotenuse. And yes, the hypotenuse is always adjacent as well. So it's kind of a weird naming thing that they came up with. No one ever has to have the sines, cosines, tangents memorized. You might have them memorized. You might have SOHCAHTOA memorized. We will always give you what the sine, cosine, tangent equations are. We have no interest in having any of this memorized. We are only interested in the application of this. We often will actually have the triangle written out as CBA, C being the hypotenuse, A being the adjacent, B being the opposite. That's just the traditional way of writing it out. And so you'll always see that sine theta is B over C, cosine is A over C, and tangent is B over A, which is just still opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. So SOHCAHTOA is still being used. We're just using different nomenclature here. And for those who are up with Pythagorean theorem, C squared equals A squared plus B squared. That's also a base equation that you will get. You'll never need to have that memorized. But again, being able to use it is another story, and that's the important skill set that we're going to be working with. So a typical situation that you would see is something like this, where we're given the hypotenuse, and I just want to find the opposite side, and I know the angle is 36.87. So I'm going to just start with my sine, because the sine is the ratio of my opposite over my hypotenuse. Those are the two sides I'm working with here. And so I'm going to say the sine of 36.87. Now, the people who get gummed up in trigonometry look at this and think that this is some special thing, some operation. I don't understand what's going on. But when I see this, I don't see anything other than a simple ratio that I don't have to have memorized. I'm going to just simply use my calculator, and it's going to turn around and say, oh yeah, that's just 3/5. That's the ratio that you're working with. There's an imaginary similar triangle that we can use. So just 3/5 is equal to y over 300, so y comes out to be 180. The calculator often puts this in decimal form, which is totally fine. So instead of saying 3/5, I might see it as 0.6. But either way, y comes out to be 180 because a fraction and a decimal are really the same thing. When dealing with triangles, we love working in degrees, and that's the most common unit that you've worked with throughout most of your mathematical education. We know that if I have an XY coordinate system, the angle between two axes is 90 degrees. That makes it called a right angle. Nice to know that for a complete circle, it's 360 degrees. And so we're not going to spend much more time on this because you guys already know degrees. It's not that big of an issue. However, when we deal with a circle, degrees aren't exactly beneficial. Simple reason is when I draw out my triangle, my right triangle, that doesn't relate to the arc of the circle. So if I was interested in this part of the circle, this angle in degrees isn't helping me. If this was 45 degrees, then I know that this distance and this distance are the same, but neither one of them is the radius. And it tells me absolutely nothing about this arc length on the circle. So we need to have a different unit of angle that relates specifically to circles. And so what we do is we expand out from a triangle to more of a pizza slice, if you will, where we have the arc being connected by two radii. The angle needs to have some sort of relationship with this distance. And when we expand out my radius, I do see that my arc distance gets larger. And just like with triangles, where if the angles are the same, I have similar triangles, and thus I have a ratio that I can use because they're all proportional. I have here similar pizza slices because their angles here, here, and here are all exactly the same with one another. So I can use the same kind of logic with similar triangles as I do with these similar shapes. So there must be some proportionality between the distance of my arc and my radius when dealing at the same angle. So we define now a new unit known as a radian. 1 radian would be some angle on where my arc distance and radius are exactly the same size. We're not going to really worry about that. We're going to just turn around and say, every time I'm dealing with a circle, we're going to work with so many radians. And it's just a number, just like degrees. And we're not going to make a big deal about that. Because again, it's going to be more about the application. So we can easily say that this theta must be a ratio of this arc length and this radius. And that's all we're saying. This theta is a ratio of my two sides of my pizza slice. Often we're more interested in this delta S, the arc of the circle, so we rewrite it as delta S equals delta theta R, but it's really the same ratio as before. Again, the unit that we're talking about here is called a radian, or RAD, rad, for short. Okay, and a radian is again just a ratio of the arc length to the radius and nothing else. You've actually worked with this in the past. For example, if you think about the circumference equation, the circumference is just the arc length of an entire circle. And we know that circumference equals 2 pi r. But here's the funny thing. What really is 2 pi? For most people, they think it's just some random number that just is used to find the circumference. But the reality is, it's an angle. It is the eighth, it's the angle of a complete circle in radians. So if we were to be very honest about the circumference equation, it's not 2 pi r. It's 2 pi radians times r, where radians is an angle. And if we think about it, circumference is just an arc distance, so that's delta s. 2 pi radians is an angle for that arc distance, and radius is radius. So if you've worked with this equation before, you've actually worked with delta s equals delta theta r. You just never realized it because people talked about the full circle and not just a section of it. For any complete circle, the angle is always 2 pi radians. So this means we can come up with a simple conversion factor between radians and degrees. So since a full circle is 2 pi radians, and that's also 360 degrees, we can say that 2 pi is equal to 360 degrees. Or for half a circle, that would be pi radians, half of 2 pi, and 180 degrees, which is half of 360. So our conversion factor from radians to degrees is pi radians equals 180 degrees. We actually will not be doing a whole lot of converting from one to the other, but you might be put in a situation where you'll have to convert from degrees into radians or vice versa. Simply because a lot of times people feel it's easier to work with degrees than radians for visualization, because most of us can easily picture 90 degrees, or we can picture 180 degrees, or we can picture 30 degrees. However, when you turn around and say, yeah, I've got like half of pi radians, that's not easily visualized. Now, if you're going up, nah, that's 90 degrees and I got it. You've actually recognized it's 90 degrees and you're picturing 90 degrees, not pi over 2. For example, if I said 1/6 pi radians, I have no idea what that looks like, except I know it's smaller than 2 pi. A big difference that we're going to be seeing when dealing with our angles is in math, a lot of times they have you reset. The bottom line is the values of sines and cosines are cyclical. They always repeat. Once I get to 360 degrees, it's just like I'm starting all over again. So if I take a look at the values of a sine function, I can see that at 0 and 360, they're exactly the same. And at 720 degrees and 1080 degrees, they're always exactly the same. And they always do the exact same behavior. So mathematically speaking, if something rotated half a cycle, or if it rotated 1,001 cycles, I really wouldn't be able to tell just by looking at two pictures of them, and their values would be exactly the same in terms of their orientations. And so a lot of times math teachers will have you reset every single time because it's just easier to work with 90 degrees than 1,170 degrees. Same thing with the cosine. But in physics, we can't really do that. And the reason for that is, while in math, you're looking at an object that's just rotating in one spot, and you're only looking at orientation, kind of like a person, if you will, that is supposed to stand still. And when you watch them, they're standing still. But then when you turn their back, they start to run around. But as you start to turn to see what they're doing, they return back to their original spot in position. You would just think they're always standing still. Well, we know they're actually moving. We're going to have a similar situation here. If I have a wheel that's going to rotate, and it rotates one time, it rotates 2 pi radians. and it will travel a distance that is the circumference, which is 2 pi radians times the radius. That's not the same thing as standing still. There has been a tangential change. If I roll 2 times, I go further. Now I go 4 pi radians times the radius, double the circumference. So we can't ever reset for the very simple reason there's going to be other aspects that will not repeat out. So we have to always keep the same angle. So if we have something that rotates 5 times, then I turn around and say that's 10 pi. I can't say that's 0. It's not exactly the same. Angularly, yeah, it's going to be equivalent. But when we actually take a look at distances traveled, things that have been pulled, it's going to be very different. And so there is never any resetting, which actually makes our life easier because whatever angle you find, that's your answer. You don't have to sit back and go, well, now how many rotations is that? How much do I have to subtract out? We have a lot more freedom because we don't have to reset. Also, we have to talk about pi real fast. I know in math class they are very big about making answers that are totally and utterly exact. So if you have something that's 2 times the square root of 2, your answer is 2 square root 2. And if you've got something that's 4 pi, you say 4 pi. And you have to leave the square root, you have to leave in terms of pi, because these numbers are irrational, they don't have an end, and you want to be exact as possible. That's not realistic. Okay, if we turn around and say how tall, ask the question, how tall are you? And you give us a measurement, is it really exactly 100% on, or is it fairly close? And the truth is, it's fairly close. Once we get that down to a millimeter of size, we often don't care about anything else. We just consider it to be, any difference to be ignorable. So when we deal with pi, we're going to work with 3.14. So we're never going to actually have answers in terms of pi because it's not practical. So that's going to be a key thing. Just like when we turn around and work with the math question 2 times the square root of 2, our answer will not be 2 root 2. We're going to turn around and say root 2 is 1.414 and just call it quits and say, well, 2 times that is like 2.828. There's a whole lot more to it, but those values are so small, we just don't care about it. And so, again, we're going to be dealing with practical applications rather than the ideological. So here's a typical situation that we're going to probably see, where we have a wheel that's going to, with a radius of 2.5 feet, it's going to roll across the floor rotating 10 times. And I want to know how far did it roll across the floor. So I know the radius is 2.5 feet and it rotates 10 times. Each rotation though is 6.28 radians, which is 2 pi. Remember, pi is 3.14 for us. This means that the change in angle for the entire 10 rotations is 62.8 radians. Simply using the arc distance equation, delta S equals delta theta R, I can find the distance traveled. 62.8 radians times 2.5 feet. The radius equals 157 feet. That's how far it traveled. I'm not really looking for the circumference. I can easily divide that by 10, see it's 15.7 feet, but that's irrelevant to what we're looking for. We're going to keep things really basic and just simply use the tools that we have. Again, this is something that I do not need to have memorized. I am given this. I just need to know really that for a circle, it's 6.28 radians. All right. I hope this starts to make a little bit of sense for you guys. If it doesn't, that is totally okay. This video's function is just to get you introduced to what we're talking about. When we meet in class, we're going to be working on this much more in depth. So at no point am I going to turn around and say, if you have a question in class, oh, you should have seen that in the video and we're done. No, not at all. So if you saw this and you know this all, great. You are ahead of the game. If you're looking at this saying it kind of almost makes sense, but I need practice, you're exactly where you need to be.